Thank you so much for having me. This is actually my first Women in Data Science conference, so I'll have to be sure to get one of those wonderful selfies after we're done with this. All right, so I'm going to introduce you to the Bayesian causal framework, but before I do that, just a little bit about me. My background is in statistics, so formal training from Florida State University. I spent a lot of time in various industries across government, academia, as well as pharmaceutical industry. I mostly worked on uncertainty quantification, design of experiments, and density estimation, particularly with non-parametric methods. And then I kind of honed in my skills on Bayesian methodologies. So what made me think about discussing causal inference? Right now, we hear a lot about generative AI, and for good reason, right? These solutions are advancing technology as we know it and making a lot of our lives much, much easier. But I bet that a lot of the researchers who are building out these solutions have started to think of, how do I understand the causal structure of the data underlying my problem? Right? Considering these things helps us to make these solutions more robust, more interpretable, and even fair, right? And so, second to that, you also want to think of, well, you said something about Bayesian. Well, I'm just partial to Bayesian methods, right? And so why not put a Bayesian spin on things? And so in order for us to understand what I mean by causal inference, we might think of how we think of the relationships of data. Right? Typically, in our everyday lives as statisticians and data scientists, we might use statistical relationships, meaning we have some observational data. We get that data, we find a set of predictors, we put those predictors through a model, and we get some predicted outcome. Now, oftentimes you might hear of this model as like a black box, right? And this is just a loose term used, but when we're saying this, we're just saying we don't have an inherent structure or directionality that helps us understand the inner workings of the relationship between our predictors and our outcome, right? When we're talking about causal relationships, we kind of want to remove this idea of the black box, meaning we want to know what's happening under the hood, right? Can I understand the directionality of these predictors and the outputs? Now, this is not to say that statistical relationships should be null and void and we shouldn't use them, right? I use them every day. We will continue to use them every day, and quite often they're very important, right? Causal relationships just help us to answer the question, well, what happens when we need to make a change in our predictors, right? If I make a change for what goes into this model, how does that underlying model structure change, right? We don't know, and especially if we're trying to make that change in real time, right? So of course you might say, well, I can just add another predictor and get an output. Absolutely, but how did that predictor change your model, right? We don't know when we're assessing statistical relationships. So you might hear two different languages when we're talking about causation. The first, you might hear the term counterfactuals, and the other is causal graphs, or what's often known as intervention, right? And we can talk about these scenarios in two different scenarios. Let's say that you're a kindergarten teacher, right? And you're assessing reading levels. You look across the school and you're like, seems that the shorter children have lower reading levels and the taller children have higher reading levels. So you send a note home and you tell the parent, stretch your children, right? So they do that. The children come back, you assess their reading levels, and to your not surprise, nothing has changed, right? The reading level has stayed the same. Now, there was an association, right? I think we can all agree if we go to a local elementary school, we might see that the little pre-kindergarten students are on a lower grade level than the older children who are in 5th grade or about to head on to junior high school, right? Makes sense. So with that in mind, we might even then say, well, I can use height to predict reading level. Makes sense, right? But what that does not mean is that height caused reading level. Now, under the causal graphs or intervention, we might have this type of scenario, right? We know that there's an association between smoking and lung cancer. We also believe that smoking causes lung cancer, right? There's been several studies, nationwide campaigns of the same to support this claim, right? And so with that in mind, we might say that, well, if I intervene, right? If I force a person to smoke, this might change their probability, or this will change their probability of getting lung cancer, right? And so the difference here is that we forced an intervention. Under the causal graphs and intervention, we think of this as doing, right? What if I do, and how? How does X change? How does Y change if I do X? And so these two ideas, right, lead us to what's called the potential outcomes framework, asking the questions of what if? What if I had done? What if I do? And this potential outcomes framework is not new. It was developed many, many, many years ago. And it just is an entire framework that helps us to understand how we think of causal relationships, and then to go ahead and kind of define those causal relationships such that we can build an inference on them, right? And so the first thing says that causation requires manipulation, meaning you have to have something that can be manipulated, something like an intervention, maybe a treatment, right? Something that we can force to happen and force not to happen. Our goal here is to estimate the effects of the cause and not the cause of effect, right? How did my change in Y cause, how did Y cause my change in X? All right, and then finally, we have three different components. We have an assignment mechanism, meaning we have a way to actually assign our treatment to these potential outcomes. And then finally, we have a model for the science, meaning we need a way to model each of our variables, right? And in this talk, we'll talk about that in the Bayesian paradigm. Right, so let's go through an example, and this is the example that we'll kind of use throughout the entire talk. Right, consider that you are a data scientist at Microsoft, and you are asked to analyze some data on Azure compute hours, right? And this is just the number of time a person spends using our popular platform, Azure, right? And you have these data for days that there was a free trial available, and you have data for when the free trial was not available, right? And so the very first thing you do is say, hey, I'm going to do some EDA, and you plot the data. And now you look at this and you might say, well, this looks good, right? It seems that there was an uptick on the times that the free trial was available, right? There was an increase in usage there. But of course, you can't give that to your manager, right? You're a data scientist. You have to do some formal statistical modeling or something on it. So you say, I can just do a simple logistic regression, right? You do the logistic regression, and sure enough, you come to the same conclusion. Azure free trial leads to increased usage. Right, great. Go give everyone an Azure free trial. But then you have to think, did I account for everything, right? And as data scientists, we quite often see this, right? We're not a part of the clinical team. We're not a part of the marketing team. We're not a part of the sales team, right? So there's almost always something else that we need to consider, right? This is what makes our work so interdisciplinary. What we didn't know was that Microsoft launched a new service. It was a virtual fashion designer. Great for Microsoft, right? They launched, what was bad for us was that they launched this new service at the same time that they started the free trial period, right? And so it might have made sense, right? Hey, offer a free trial. When we launch this service, it will increase intention. People will use it. You want to try it out before you buy it. Makes sense. But for us as the data scientists, we have a confounder, right? Now we're left with trying to understand, was it truly the Azure free trial that increased usage? Or was it actually the virtual fashion assistant that caused the increase in usage, right? We don't know. How do we figure this out? Now you might immediately look at this and say, well, Danisha, Randomization, right? We see this all the time, right? We can do A/B testing. We can run a randomized control trial. And while these things are true, right, and what I mean when say we do randomization is we essentially just break this relationship, right? And we leave the increase in usage up to the user, or up to the data scientist, I should say, right? We control how these things happen, right? That's what happens when you do randomization. But what we also know is that randomization is extremely costly, not only financially, but in terms of time, right? The people that have to go into it, right? We also think of ethical considerations, right? We know, especially in things like clinical trials and life sciences, we cannot give one group a lesser efficacy drug or something like that, right? When we're thinking about recommendation systems, we cannot train only on fair skin, right, and not train on darker toned skin, right? So then for our specific case, we have this data already, right? We're past the step of designing of an experiment, right, and designing in something in such a way that we can do randomization. No randomization was done on this data. So we have to consider a way that we can generate what we thought would happen or what could happen. We need a way to generate those what-if scenarios. And we can do this with what's called the data generative process. This data generative process essentially provides us a way to write down how we think of the underlying structure of our data. And so in this case, we might have some confounder, C, right? And for us, this was the launch of that virtual fashion assistant, right? And we might even go on to say, hey, if I'm speaking in terms of data, I think that this variable is just going to be some normal with 0, 1, right? Meaning a person can spend as much time in this virtual fashion assistant as they want to. Of course, how much they want to pay for, but as much time as they want to. And then we might have Z, right? And Z represents whether or not that free trial was active, the Azure free trial was active, right? And so we might think of this as Bernoulli, right? And we have this inverse logistic here just to make it a logistic, right? Scaled between 0 and 1. That's all this is saying. Logistic scaled between 0 and 1. But then we want to add an intercept, beta Z naught. And then finally, this piece, beta ZC, helps us to understand our influence of C on Z, right? What was the influence of this virtual fashion assistant on using Azure during the free trial period, right? And then finally, we have Y, right? And Y, again, represents just the total compute hours that we were using, in Azure. And we might, again, think of this as normal with mean, or with that as the intercept, plus beta ZY, right? So this is going to be the relationship between, or the influence of Z on Y. And then finally, plus beta CY, which will represent the influence of C on Y, right? And so this little structure that we have to the left here is what's called a DAG, directed acrylic graph, right? And so you might have seen these. And there is an entire area of study that goes into how we even write out these DAGs, right? As you can imagine, we have a single confounder here. We could have many, right? We could have many other predictors, right? So these things get really complex. And one very specific type of graph is DAG is the Bayesian network, right? And all it says is the Bayesian network is going to consist of 2 parts. The first is going to be the DAG itself, which we call the structure. And then the second part are going to be our parameters, right? And it says that these parameters, we're going to be able to put some probability distribution on them, such that we also have priors that help us to understand how we think of the strength of the relationships, right? And so again, all of our betas is what's helping us understand the strength of these relationships, right? And so you look at this and you're like, well, this looks like normal Bayesian inference to me, right? I've seen this before, right? I put this into some software, statistical software, and I generate my data, right? What we're doing is generating y. And in this generation process, I'm going to get posterior distributions for all of my unknowns, right? All of these betas that represent the strength of this relationship. And so normally we might stop there, right? Because in traditional Bayesian inference, that's what we're trying to uncover. We're just trying to get these posterior distributions of our unknown data. But we have to remember, we still have more unknowns, right? We have Z, we've uncovered it, we've generated for Y, we've generated for C, right? We figured out our betas using Bayesian inference, but we still have these idea of potential outcomes, right? And so again, just like we saw earlier, right? Just like we see in normal Bayesian inference, we have our model, we have some priors, and then we use those two to get our posterior distribution, right? And under the Bayesian causal inference framework, we can carry out those same steps. How do we use the data that we have to generate our unknowns? We have two additional unknowns, right? So again, let's think through everything that we have. What are our four quantities, right? We have our two potential outcomes. We have Z, which is our treatment, and we have C, which is our confounder, right? And so be mindful when you see these zeros and ones, right? These just represent our outcomes under a specific treatment, right? And so for every unit, right, for every customer we might think of in our example, we'll always have at most one observed possible outcome, right? The other is going to be missing or counterfactual, meaning we either observed the outcome when the treatment was present or we observed the outcome when the treatment was missing. And we can think of the joint relationship between our potential outcomes and our treatments as Y observed or Y missing, right? So we can jointly use these to figure out our observed and missing values. And so with this, right, we can now draft the model. And if we think of our potential outcomes framework again, right, we need a model, we need our potential outcomes, and we need an assignment mechanism. Right, so we might think of the joint distribution as the probability of our two potential outcomes, Z and C, as factorized into three different parts. The first being our assignment mechanism, the probability of Z given our outcomes in C. Now, under ignorability, those two possible outcomes would just fall out, right? So what you're left with is the probability of Z given C. And then we have our potential outcomes, right? The probability of our outcomes given C, our confounder. And then we have our covariates, which is just C itself, right? The probability of C, right? And so if we're thinking through that DAG structure, right, and how we wrote out those distributions, this makes sense, right? It seems to align. Now you might say, okay, well, that's good, but how do I get now to my potential outcomes, right? How am I generating the data for Y0 and Y1, right? What we can do is, you want to remember that we already have estimated we already have posterior distributions for our unknowns from the original data, right? Meaning, so we have no more unknowns there, right? We know all of our betas, we know Z, C, and Y, right? So what we can do is use the posterior information there under our two potential outcomes. Under Z to get our two potential outcomes, right? And now there's like a nifty new tool in most computational statistical softwares now. This was not available back when I was learning WinBugs and JAGs, but we have what's called the do operator, right? And all this do operator says is keeping all other things to be true about my original model, right? Meaning take into consideration all of my posteriors. What happens if I set Z to be 1? What happens if I set Z to be 0? right? And so how it's acting is like a physical intervention, right? Use my posterior estimates and help me to uncover unknowns. Why? Because under the Bayesian framework, all of these values, y0, y1, z, and c, are just random variables, right? And we know in the Bayesian framework, random variables are unknowns, right? And we can get their posterior distribution. We can get posterior inference on them, right? And so we treat them no different. We treat them like unknown variables, right? And so we can generate two new distributions, right, that will help us to understand the probability of y under z0 and the probability of y under z1. So what we've done was we wrote down our DAG, right? So we know the underlying structure of our data. We've provided some posterior distributions onto this data, right? We have our, I'm sorry, not posterior distributions, probability distributions on these values, right? And we've provided some prior knowledge of how we think about the strength of the relationships. And then finally, we use all of the posterior information from our original data to help us uncover our unknowns, right? To help us estimate our potential outcomes under the do operator, right? And so you might think that's it, right? The prediction wasn't good enough. They came back and they said, well, we actually have a confounder. I uncovered it. I provided two different outcomes, right? I've shown what happens under our two scenarios, right? But have we truly answered the question at hand, right? Now you have to ask yourself, number one, what is the recommendation here? Well, you gave me the two distributions. I know what potentially could happen, but should I be using the Azure free trial? Should it be turned on or off? And then once you give me that recommendation, are you sure, right? How sure are you in the recommendation that you've provided me, right? And we got to think of this in terms of policy making, right? Things that can affect nations, right? Things that can affect women, right? So there are two types of uncertainties that we generally see. We see aleatoric uncertainty, and then we see epistemic uncertainty, right? The first is more talking about observed data, and the second is more on model data, right? And I would argue that, we won't go really into the uncertainties, but the important part here is that as you're thinking about, well, what uncertainty should I be using for my model, right? Am I trying to uncover or talk about model uncertainty? Am I trying to uncover or talk about data uncertainty? The more important question is, how will this uncertainty be used, right? What will be the use of this uncertainty when you're providing your deliverable or you're writing out this policy, right? Because what we see, especially oftentimes in the physical sciences, is that we can't just only rely on our model uncertainty, and we can't only rely on our data uncertainty. There are oftentimes other factors, outside factors, that we must consider when we're trying to devise and say, hey, this is the uncertainty in the recommendation that I'm providing, right? So more about why in the use of the uncertainty than it is to uncover what type of uncertainty I should be discussing, right? And so the first piece is the recommendation, right? How do we first come up with a recommendation? We have various causal estimates that are used, particularly in the scenario that we kind of discussed here. But the one we'll discuss, or the one we'll uncover, is the population average treatment effect, right? And all this is saying is, if I were to randomly choose a group of customers, what is the average treatment effect that I would expect, right? And it's a very simple calculation, because if you recall, we have a distribution for each of our potential outcomes, right? We have a distribution under 1, and we have a distribution for our outcome under 0, under treatment 0, right? And so being that we have these two distributions, we can compare them and get another distribution, right? That is a beautiful thing about Bayesian inference, right? We're not just getting point estimates, right? Throughout this entire talk, we've gotten distributions, an entire distribution for everything that we've estimated, right? And so if we were to use these two distributions, compare them, and calculate their expectation, we might get something that looks like this, right? And so this is a picture from a Python software package, right? And so we get an entire posterior plot, right, that helps us understand our average treatment effect, or what we would expect, right, if we were to just sample a small group of customers, right? What would their average treatment effect be? We also can plot their potential outcomes, right? And we see a change in the potential outcomes because if you remember, we said that there's some influence of C happening on Z, right? So we're going to expect as the days go on, we see an increase or decrease or just a change in general, right, of these potential outcomes, right? So we are left with an entire posterior plot that helps us understand our average treatment effect. We have a credible interval around our estimate, right? And so now we can provide some level of uncertainty to the recommendation that we're given, right? We can now say how sure we are in what we've uncovered by generating our potential outcomes. Right? And so why Bayesian causal inference versus just causal inference, right? Causal inference says, given the data, what are plausible structures of the model that were generated by this data? The important piece for the Bayesian inference framework is that we are interested in the expectation and uncertainty around the parameters that generated this observed data, right? So not just the model and the underlying structure, but the parameters that made up that model and the uncertainty estimates around those parameters, right? And so hopefully in this short time, I have given you a really good reason to go and say, how do I incorporate Bayesian inference to answer my what if questions, right? How do I uncover if my data has confounders? How do I ask what if and what if I had done? Right? Now, what we didn't go through were a lot of the limitations, right? Bayesian is a beast in itself, right? So on top of getting a grip on causal inference, you also have to understand some of the basics of Bayesian methodologies, right? And so, of course, it's computationally complex. Again, you all have like really fancy softwares and packages in Python. We did not have that, right? So the computational complexity is getting a lot better now. You have to be able to specify your model, right? You have to be able to conceptualize how you think the data looks, right? You have to be willing to collaborate. Again, because we're providing prior information for how we think about the data, this means you have to talk to some people. Hey, in a clinical setting, what typically happens in this situation, right? You have to be able to ask those questions. We have some assumptions of conditional independence. You have to worry about data quality, right? Your estimates are only going to be as good as the data that you're providing to the models. And then, of course, as we mentioned earlier, the causal structure, right? It can be very complex. We went through a very simple case where we have one confounder and one treatment, no other covariates, right? But of course, in our day-to-day lives, it might not be this simple, right? And quite often it won't be. And then finally, interpretability, right? Understanding and being able to talk through the results we get from Bayesian models can be quite difficult, especially when you're dealing with other distributions, right? Gumbel distributions, extremely skewed distributions, right? How do we interpret and explain our findings, right? So a lot of challenges, but still, I'm in support of the method, right? So thank you so much for having me. I'll take any questions.